I'm Aditi. I'm a backend and infrastructure engineer at Offline Protocol. And today I'll walk you all through how to architect event-driven blockchain app dApps using off-chain microservices. Yeah. So I was saying, when we talk about Ethereum applications, what we usually think as new developers is the user sends a transaction to the contract updates the state, and then the front end reads back the data from the blockchain. So the mental model here becomes write to the chain and read from the chain. But the reality of production Ethereum applications is quite different. The modern dApps that we use on a daily basis, like DeFi dashboards, leaderboards, notification systems, or analytics, a platform, social feeds, etc., those are powered through, like they are not actually querying the blockchain on every refresh. These applications are powered through a pipeline of off-chain services, which are indexing event data, blockchain event data, and then processing it into a useful application state. So smart contracts don't run applications alone. Infrastructure does, which means we have a couple of services that are running full time to provide you the data instantly, which involves event listeners that are listening to the chain, that are tracking events, queues that are buffering blockchain data, and worker services that are picking that data from the queues and then processing however you require. And then we have APIs that serve fast responses to the user. For example, Uniswap doesn't query the blockchain on every refresh, or any other application that you use does not query the blockchain for any read transaction. So when we can actually query, why do we have to build all this off-chain services, all this complex infrastructure? Because first of all, Ethereum is not request response. You cannot ask the chain that give me all of the user transactions for this particular smart contract, or the last. You cannot ask the chain, give me all of the borrow positions for this protocol or anything like that. Because you'd have to store that in the contract, and that requires gas. We don't need to do that. We have events for that. For example, in an ERC20 contract, this transfer event becomes the only efficient way to track token balances, to detect payments, and monitor activity. So yeah, now these events, the example that I showed for the ERC20 was written in Solidity. Taking the example of Solidity, events are somewhat initialized like this. We can see that some parameters have a field called indexed. We'll come back to that later, but on an overview, Solidity events make a data layer that is structured, efficient, and immutable, meaning that it has a defined format. Efficient means it is queryable via Bloom filters. And immutable means, of course, everything on the blockchain is immutable and stored permanently as transaction receipts. Okay, so why do indexed events matter? First of all, you cannot continuously scan the chain for whatever data you want. When you index a particular field, you can just, if, for example, you want a particular user's transactions. So those, you can initialize a filter for that using these indexed events. Now, I'll not get into the programming details over here, but yeah, you can use the index fields to basically filter your events however you like. Now, but the only constraints that the index fields here are, you can only index 3 fields per event. There can be no range queries. That means you are not allowed to query based on numbers. That means you need an amount greater than 10,000 or something like that. And you must filter off-chain, of course. So for this filtering off-chain, you can write event listeners using Rust, Go, Python, or TypeScript, any language that you prefer. So I would divide the architecture into 3 phases. First phase being ingestion, which means capturing blockchain events. And this architecture basically involves the first is the Ethereum node. That is, of course, the source of truth for our transactions. Second would be the event listener, which, of course, I mentioned that we can write that using any language preferred. This event listener will constantly listen for the transactions happening on chain, and then it will transfer it to the queue, which is the message broker over here. And that queue is basically responsible for absorbing the spikes that can happen in your system or anything, like your workers can consume it through the queue. So phase 2 would be processing, transforming events into application state. Here, what we do is pick up applications from the message broker, and the worker services can process it however you require. Suppose it is a lending protocol, and you want to group transaction based on a particular user. So worker services could do that and then put it into a state database from where your front end would actually use it. Now, worker services can be horizontally scaled, meaning each worker there could be multiple workers, and those could process events asynchronously and parallelly. Okay, next. The phase 3 and the final stage of this architecture would be consumption. And this happens basically on the front end side, where a user needs particular data and they query the whatever API endpoint they have. This is then fetched through the state database. For example, leaderboards. So top 10 users of this week. It's fetched through the database and then showed it on the front end. This also involves WebSockets, optionally, if you want real-time data, which could be price feeds or anything like that. So, yeah. Talking about the performance and reliability over here, there are certain problems to handle while designing for scale. And that is, there could be duplicate events. This can happen because of RPC nodes going down, or you are using, suppose, multiple RPC nodes to index transactions, and one of them or two of them just mix the transactions in your event listener. So it is important that the solution here be idempotent to workers. Means if you compute the same event again and again, the output should result in the same thing. Suppose you're calculating like token balances, and there is a transfer event from my account to your account. So it is important that if the event is processed again, it should not result in my balance being twice minus, and then yours would be like gained 2 times. So that is why idempotent workers are important. Then there could be out of order logs, just as duplicate events. These could happen. And then event versioning is important for that. Then there are chain reorganizations that take place. So we also have to maintain like block number checkpoints. Like we processed, suppose, a 10,000 number block the last time. So if our event listener goes down, or suppose RPC node goes down, we have to start processing from the 10,001 block again. So making sure this is done. And then there are RPC node inconsistencies again. So we'll also have to maintain replayable pipelines. Means you should be able to compute the state again as it was earlier. So considering a lending protocol example, how this would work is we've all used a lending protocol at some point. So the user transacts with the lending protocol. The contract processes the transaction, the event is emitted, and then the listener detects it. After the listener detects it, it puts it into a queue where it can be there for some time. And then whatever worker is present, is idle, can pick it up. It recalculates all of the processing, and then flags if there is a risk involved, or updates the API dashboard accordingly. And then, yeah, I mean, this data can be queried multiple times by the front end. It would still be the same as it is in the state database, and also it will be cost efficient and also fast. So, thank you.